Welcome. There is nothing to do now but rest. Let your shoulders sink into whatever is holding you. Let your breath slow without trying to slow it. Tonight we drift toward the edges of everything, and back again, and there is no place you need to arrive. The observable universe stretches about 93 billion light-years across. That number describes only what light has had time to reach us. Beyond that horizon, space likely continues, quiet and unseen. Every star you have ever noticed sits inside this modest bubble. The rest simply waits beyond our sight, patient and unhurried. Roughly 13.8 billion years ago, the universe began. Time itself seems to have started then, not merely matter. Before that moment, our usual words like earlier and before may simply not apply. Everything we know, every atom in your body, traces back to that single ancient beginning. The Big Bang Theory rests on solid evidence, especially a faint radiation filling the sky. This afterglow, called the cosmic microwave background, reaches Earth from every direction equally. It carries the imprint of the universe's early heat. Physicists read it like a very old photograph, one taken almost at the beginning of time. In 1965, two radio astronomers named Penzias and Wilson discovered this radiation entirely by accident. They were testing an antenna and kept hearing a faint, steady hiss. At first, they suspected pigeon droppings on the equipment. Instead, they had found the oldest light in existence, quietly filling the whole sky. Since its birth, the universe has been expanding. Space itself has been growing wider every moment since then. Galaxies drift apart, not because they are racing through space, but because space carries them along. It has been happening quietly for billions of years, and it continues even now, as you rest. Edwin Hubble discovered in 1929 that distant galaxies are moving away from us. He noticed their light stretched toward red, a sign of retreat. The farther a galaxy sat, the faster it seemed to withdraw. This simple observation quietly rewrote humanity's picture of the entire cosmos. This rate of cosmic stretching carries a name, the Hubble constant. It tells us how quickly space unfolds at a given distance. Measuring it precisely has occupied astronomers for generations. Even now, different methods return slightly different answers, a small patient puzzle still being gently worked out. Space itself stretches during expansion, not merely the matter within it. Galaxies are not flying through a fixed emptiness. The emptiness itself is widening beneath them. It is a strange and gentle idea that the very fabric carrying the stars is the thing quietly growing. The universe's expansion appears to be speeding up, driven by something called dark energy. Distant galaxies are receding faster than earlier models predicted. Astronomers noticed this only in the late 1990s, watching the light of ancient exploding stars. The universe, it seems, is not just growing, it is growing more eagerly with time. Let the breath lead now. Take one in, unhurried, and let it fall back out even slower than it arrived. Feel the exhale grow longer each time, a small tide going out and staying out a little longer. There is no place this breath needs to reach. Just this one, and then the next, drifting further apart, like the space between stars. Dark matter makes up about 27% of everything that exists. It cannot be seen, touched, or captured in any telescope's light. We know it mainly by its pull, the way it bends starlight and holds galaxies together that would otherwise fly apart. It moves through the night sky around us right now, unseen and unbothered by our noticing. Ordinary matter, the stuff of stars, oceans, and bodies, makes up only about 5% of the universe. Everything ever touched, tasted, or measured belongs to this small sliver. Every mountain and every breath falls inside that thin slice of existence. The rest of the cosmos is built from things stranger than anything our hands have known. The cosmic microwave background is the leftover glow of the universe's very first light. It fills every direction of the sky, faint and even, like warmth, lingering long after a fire has gone dark. This glow has been traveling since the universe was new. Tonight, some of that ancient light is still quietly arriving, though it can no longer be seen with human eyes alone. That glow was released about 380,000 years after the universe began. Before this moment, no light could travel freely through space. It was as if a fog had lifted all at once across the entire cosmos. The universe, in an instant, became transparent, and light finally had somewhere far to go. Before that clearing, the universe existed as an opaque plasma, thick and glowing, impossible to see through. Electrons and light were bound so closely together that no photon could travel far before being scattered again. It was less like empty space, and more like standing inside a bright, endless storm. Nothing could see beyond its own small reach. The early universe was extraordinarily hot and dense, packed tighter than anything we could easily picture. In its first moments, temperatures soared beyond what any star could reach today. All of space, if space is the right word for something so small, held more heat than trillions of suns combined. And then, slowly, across billions of years, it cooled. General relativity describes gravity not as a force pulling objects together, but as the curving of space-time itself. A star or a planet bends the fabric around it, and other objects simply follow that curve. Light itself bends along these paths, tracing invisible valleys carved into space. It is less like pulling and more like rolling gently downhill. Einstein's field equations, written to describe this curved spacetime, quietly allow for universes that grow. Solved a certain way, they describe not a fixed cosmos, but one stretching outward through time. Einstein himself resisted this idea at first, favoring a static universe. Yet the mathematics kept pointing toward motion, toward expansion, toward change. The Friedman equations take those same principles and map out how the universe's expansion has unfolded across time. They describe a cosmos that can grow, slow, or even someday change its course depending on what fills it. Matter, radiation, and dark energy each play their part in this long calculation. Within these few lines of mathematics rests the entire shape of cosmic history. Deep inside every atom, particles behave by rules that defy ordinary experience. An electron does not travel a single path, but exists as a spread of possibilities until observed. Physicists call this superposition, a haze of potential outcomes collapsing only when measured. At this scale, certainty gives way to probability, and probability governs everything. Let your legs grow heavy now, sinking into the mattress the way sand settles at the bottom of still water. Feel that weight travel upward, through your hips, your back, spreading like warmth through a cold room. Your shoulders no longer need to hold anything. Let them drop. Let the bed take all of it. Every part of you is being held, resting fully, needing nothing more than to stay right here. Physicists eventually merged quantum mechanics with Einstein's special relativity, producing quantum field theory. In this framework, particles are not tiny billiard balls but ripples in invisible fields stretched across all of space. An electron is simply a disturbance in the electron field, appearing and vanishing as energy allows. This marriage of ideas became the foundation for nearly all modern particle physics. Every particle we know of fits into a single, elegant framework called the Standard Model. Quarks, electrons, neutrinos, and the forces that bind them all find their place within it. It has been tested with extraordinary precision, matching experiment after experiment. Yet even this remarkable map leaves gravity and dark matter unexplained, hinting that more remains hidden beyond its edges. An invisible field fills all of space, and its presence gives particles their mass. Physicists call it the Higgs field, a subtle background that particles push against as they move. Some particles interact with it strongly and become heavy. Others pass through almost untouched, remaining light. Without this field, matter as we know it would simply fly apart at the speed of light. In 2012, researchers at CERN confirmed the existence of the Higgs boson, the particle tied to that invisible field. It had been theorized decades earlier, but remained undetected until the Large Hadron Collider produced enough energy to reveal it. The discovery completed a piece of the Standard Model that had waited nearly 50 years for confirmation. It was a quiet triumph, decades in the making. Deep beneath the Swiss and French countryside, machines briefly recreate the conditions of the universe's earliest microseconds. Particles collide at tremendous speeds, releasing bursts of energy dense enough to mimic that primordial heat. For fractions of the second, tiny regions resemble what all of space looked like just after the Big Bang. Then the energy disperses, and ordinary particles reappear once more. Placeholder. Placeholder. Wack Indus story actions, of course. Flatness and uniformity across the observable universe find a natural explanation in inflation. Without such a mechanism, the universe's geometry should have curved sharply, and distant regions should look nothing alike. Guth's proposal solved this by stretching a small patch of space so quickly that any curvature flattened out entirely. Regions once close together were carried far apart, yet kept a shared, uniform temperature. The evenness overhead into night sky is inflation's clearest signature. The inflaton is the name given to a hypothetical field thought to have driven this expansion. It carried enormous potential energy that pushed space outward at an extraordinary rate. As the field rolled down its own energetic landscape, that stored energy converted into the particles and radiation filling today's universe. No instrument has ever detected the inflaton directly. It remains, for now, a mathematical idea inferred entirely from its effects. Somewhere beyond the window, a sound rises and fades, perhaps wind moving through unseen branches, or the low hum of a house settling into night. You don't need to name it. Let it arrive, hold for a moment, and drift away again, the way distant sounds always do. Your breath can follow that same rhythm, rising, releasing, rising again. There's a whole world out there, humming to itself, unseen, and none of it needs you awake to keep turning. Let your shoulders sink a little further into the mattress and rest. Tiny quantum fluctuations, present even in that first instant, became the seeds of everything we see today. Inflation stretched these microscopic ripples across enormous distances, turning them into the density patterns that gravity would later gather into galaxies. Without them, matter might have spread out evenly forever, with no clumps, no stars, nothing at all to look up at. The largest structures in the cosmos may trace their outline back to something smaller than an atom. Not every region of space, in some models, may have stopped inflating at the same moment. Pockets could still be expanding somewhere, even now, forever removed from anything we could ever observe. This isn't treated as a flaw in the theory so much as a feature of how the inflaton field behaves across a vast landscape. Different patches roll down their energy slopes at different rates. Some finish quickly, others might still be stretching endlessly elsewhere. Eternal inflation is the term cosmologists use for this ongoing patchwork process. Rather than a single expansion that starts and stops everywhere at once, it pictures inflation as a fire that never quite burns out completely. New regions keep igniting even as others settle down. Andre Linde helped develop this picture in the 1980s, showing how the mathematics allowed inflation to continue indefinitely in at least some corners of space. The process, once begun, may have no true ending, Bubble universes are what this endless process could, in principle, produce. Each time a region stops inflating, it forms its own separate pocket, cooling into something like our own universe, complete with its own stars and structure. Beyond that pocket, inflation might continue elsewhere, spawning further pockets without any apparent limit. The result, mathematically, resembles an unending foam of universes, each one growing outward, unaware of its neighbors. Each of these bubble universes, the theory suggests, could settle into different physical constants. The strength of gravity, the mass of particles, even the number of spatial dimensions that feel stable might vary from one bubble to the next. Our particular bubble happens to have settled on values that allow atoms, chemistry, and eventually life to form. Elsewhere, in other bubbles, the numbers might have landed differently, producing universes unrecognizable to us. The multiverse hypothesis is the name given to this larger picture, in which our universe is only one among countless others. It draws together eternal inflation, bubble formation, and varying constants into a single sweeping idea. Cosmologists disagree about how seriously to take it, since so much of it lies beyond direct observation. The mathematics that predicts inflation also seems to predict this vastness, almost as an unavoidable byproduct. Vacuum energy refers to the lowest possible energy that empty space can hold. Even with every particle removed, space itself retains a background hum of energy, permitted by quantum mechanics. This isn't emptiness in the everyday sense. It's a specific, measurable floor beneath which energy cannot fall. Vacuum energy plays a role in cosmic expansion and, in later ideas, in whether our universe rests in a stable or fragile state. A false vacuum is a resting state that only looks like the lowest point in an energy landscape. Picture a ball settled on a wide ledge partway down a mountain, calm and unmoving, yet not at the true bottom of the slope. It can sit there for ages, seemingly stable, while a deeper, truer valley waits further down. Physics calls this condition metastable, steady enough to last, yet not the final resting place. Our universe, according to a handful of theoretical models, may currently occupy exactly this kind of ledge. The vacuum that fills all of space, the very background hum described earlier, might not be the deepest possible state matter and energy could reach. It could instead be a long-lived pause, comfortable enough to host stars and galaxies and everything else we know, without being the true floor beneath existence. A false vacuum can, in principle, decay into a truer, lower vacuum state somewhere far beneath it. Nothing forces this to happen quickly, or even soon. It would require a shift, a nudge past the edge of the ledge, letting the whole system slide downward into deeper stability. Once it began, the theory suggests, there would be no pausing partway through. Feel warmth begin at your feet, spreading upward like a slow tide through your ankles, your knees, and settling into your hips. Let it rise through your chest, filling the space behind your ribs. It reaches your shoulders next, loosening whatever the day left there. Warmth moves down your arms to your fingertips, then climbs your neck and settles behind your eyes, heavy and warm, until your whole body rests inside it. Vacuum decay, if it ever happened, would release a tremendous burst of energy, forming a bubble of true vacuum at its center. Inside that bubble, the laws governing particles and forces would settle into new, deeper values. The boundary of the bubble would glow with released energy, marking the seam between the old state of space and the new one taking its place. That bubble, once formed, would not stay small. It would expand outward, its edges racing forward at nearly the speed of light. Nothing inside its path could outrun it, and nothing outside it would receive any warning before it arrived. The expansion would be smooth and utterly without hesitation. Vacuum decay, occurring near enough to Earth, could end our universe's present form in an instant, with no advance warning of any kind. The particles, the forces, even the constants that hold atoms together would be rewritten as the bubble passed through. It is a sobering thought held gently, since nothing observed so far suggests this is imminent, or even likely, in any time frame that touches us. A few physicists have speculated, in scattered papers over the years, that vacuum decay might already be spreading somewhere in the deep dark of the cosmos. If a bubble began billions of light years away, its leading edge could still be crossing the space between galaxies, unnoticed, its arrival here unknown for ages yet. It remains speculation, resting at the furthest edge of what physics allows itself to imagine. The Higgs field carries a particular potential energy shape, and that shape is what determines whether our vacuum is stable or fragile. Picture the field's energy plotted as a landscape of hills and valleys, with our universe's current value sitting somewhere along that terrain. Whether it rests in the deepest valley or merely a comfortable shelf above one depends entirely on the exact curve that shape traces. Current measurements of the Higgs boson's mass suggest tentatively that our vacuum may be metastable rather than fully stable. The numbers place us close to a boundary line, separating a safe, enduring universe from one resting on borrowed time. The margin is narrow enough to invite careful study, yet wide enough, by any human timescale, to leave sleep undisturbed. Forming a bubble of true vacuum, in the strictest technical sense, would be equivalent to birthing an entirely new universe. Inside that bubble, the laws of physics would settle into a different, lower energy configuration than the one we currently inhabit. Everything within its boundary would belong to its own separate reality, expanding outward under its own rules. It is a strange thought. Creation not as an explosion from nothing, but as a shift in the terrain of empty space itself. Alan Guth, the physicist behind the original theory of cosmic inflation, once suggested that humans might one day create a universe deliberately, inside a laboratory. He worked through the mathematics seriously, treating it not as fantasy, but as a legitimate consequence of the physics already known. The idea felt audacious even to him. Yet the equations kept pointing toward the same startling possibility that under the right conditions, a pocket of true vacuum could bud loose and begin expanding on its own. In creating a universe in a laboratory would require compressing an extraordinary amount of energy into a space smaller than an atomic nucleus. Every joule would need to be gathered and focused with a precision beyond anything current technology allows. The compression itself is the barrier, far more than any mystery of the physics involved. Matter and energy would need to be folded into a point so dense that space-time itself would bend into a new configuration. The theoretical energy needed for this sits near what physicists call the Planck energy, a scale so extreme it dwarfs anything humanity has ever produced. It stands trillions upon trillions of times beyond the reach of our most powerful accelerators. At that scale, gravity, quantum mechanics, and the structure of space-time are thought to merge into a single, unified behavior. No experiment on Earth comes remotely close to touching it. Somewhere in a dim room, an ember dims slowly inside a cooling hearth, its glow fading by degrees no eye could quite measure moment to moment. There is no need to watch it change. It simply does on its own unhurried schedule, the way breath settles lower and lower without instruction. Let your own thoughts fade the same way tonight, glowing a little less with each passing minute, needing nothing from you but time. A handful of theoretical models attempt to sidestep the enormous energy requirement altogether, relying instead on a process called quantum tunneling. In these versions, a system might reach a new state without ever climbing the full energetic barrier that seems to stand in its way. The universe, in this framing, would not need to be pushed into existence with brute force. It might simply slip through, quietly finding a shortcut the equations allow, but intuition resists. Quantum tunneling allows a system to shift from one state to another without ever fully possessing the energy that classical physics would demand. Particles, on very small scales, behave as though barriers are not entirely solid, more like probability fading gradually rather than stopping sharply. This strange behavior has been measured directly in laboratories, underlying technologies as ordinary as certain computer chips. Extended to cosmology, it becomes a possible loophole for creating something enormous from something vanishingly small. A baby universe could, according to certain theoretical frameworks, bud off from our own through a structure known as a wormhole. In these models, a tiny throat of spacetime pinches away from the main fabric of our universe, carrying its own pocket of expanding space with it. Once separated, that new region would inflate on its own terms, growing invisibly, cut off from any further contact with the universe it came from. Wormholes are hypothetical tunnels thought to connect two distant points in spacetime, folding the space between them so that a great distance might be crossed in a single short passage. They emerge naturally from the mathematics of general relativity, appearing as valid solutions to Einstein's equations. Whether anything like them exists physically, woven somewhere into the true architecture of the cosmos, remains an open question that no observation has yet answered. No wormhole has ever been observed, despite decades of careful searching across the sky. Every known solution describing them requires exotic conditions that nature, as far as instruments can tell, has never assembled. They remain, for now, a possibility permitted by the mathematics rather than a feature confirmed in the universe around us. Their absence from every survey so far leaves them resting quietly in the realm of pure theory. Einstein-Rosen bridges are a solution that emerges directly from general relativity's equations, describing a tunnel joining two separate regions of spacetime. Albert Einstein and Nathan Rosen worked out the mathematics in 1935, long before the word wormhole entered common use. On paper, the geometry is elegant and consistent. Whether such a bridge could ever hold itself open or exist outside of equations is a separate and much harder question. Keeping a wormhole's throat from collapsing would likely demand something physics calls exotic matter, a substance with negative energy density. Ordinary matter always pulls space inward, sealing such tunnels shut in an instant. Negative energy would push outward instead, holding the passage open long enough for anything to pass through. No known material behaves this way in any quantity large enough to matter. Negative energy is not purely hypothetical. It has been measured in tiny amounts through something called the Casimir effect. Two uncharged metal plates, brought close enough together in a vacuum, are pushed gently toward each other by a force that classical physics cannot explain. The effect was predicted by Hendrik Casimir in 1948 and confirmed experimentally decades later. The quantities involved are almost immeasurably small. This subtle attraction arises from fluctuations in the quantum vacuum, the restless hum of energy that fills even seemingly empty space. Between two close plates, certain wavelengths of these fluctuations are excluded, leaving slightly less energy inside the gap than outside it. That imbalance produces a real, measurable force. It is one of the few places where the strangeness of quantum vacuum reaches directly into a laboratory instrument. Producing enough negative energy to hold open a wormhole large enough for anything to pass through remains far beyond present technology by an almost unimaginable margin. The amounts observed through the Casimir effect are vanishingly small, useful for testing theory, but nowhere near sufficient for engineering space itself. Whether any process, natural or artificial, could ever generate enough is a question physics cannot yet answer. Let your jaw soften now. the way a hand slowly opens after holding something for too long. Let your eyelids grow heavy, resting without effort, without needing to close on purpose. Behind them, everything is dim and unfocused, a private dark where no image needs to sharpen. There is only this face, unclenched, and the slow easing of every small muscle around your eyes and mouth. Black holes might, according to certain theoretical frameworks, serve as gateways rather than endings, doorways into universes distinct from our own. Instead of destroying everything that falls inward, some models suggest the extreme conditions at their core could give rise to a new region of expanding space. It is a striking reversal of the usual picture, turning collapse into a kind of birth. No observation yet confirms it. Inside a black hole, space-time curvature becomes, in theory, infinite at a single point called the singularity. General relativity's equations simply stop making sense there, producing numbers that cannot correspond to anything physical. Physicists take this as a signal that the theory itself is incomplete at such extremes, not that infinity truly exists in nature. Something else, still undiscovered, likely governs what actually happens at that depth. A number of physicists propose that these singularities do not truly vanish into infinity, but instead bounce, giving rise to a new expanding universe on the other side. In this picture, the crushing collapse at a black hole's heart reverses itself, becoming the outward rush of a fresh Big Bang. The new universe would carry its own space and time, entirely separate from the one that produced it. This idea carries a name: black hole cosmology, sometimes framed as cosmological natural selection. It suggests that universes might reproduce through the black holes they form, each new universe inheriting slightly altered physical conditions. Over vast stretches of imagined time, this process could favor universes especially good at making black holes of their own. It remains a bold hypothesis, elegant in structure, still far from any confirming evidence. Lee Smolin, a physicist working in the 1990s, extended this reasoning into a fuller theory. He suggested that universes reproduce through the black holes they generate, much like organisms passing on traits. Each offspring universe would inherit physical constants close to its parents, with slight variations. Over immense stretches of cosmic time, universes especially good at forming black holes would become more common, favored simply by their own fertility. Loop quantum gravity, a candidate theory of gravity at the smallest scales, offers a different ending to collapse. Rather than crushing matter into an infinite point, it proposes a big bounce where extreme density halts and reverses. Collapse becomes rebound. What looked like an ending becomes a turning point, the crushing motion of infall converting smoothly into the outward rush of a new expansion. Space itself, within this framework, is not smooth all the way down. Loop quantum gravity treats space as built from tiny discrete units, something like grains rather than a continuous fabric. Below a certain scale, distance stops being infinitely divisible. This graininess is what prevents true infinities from forming, giving the universe a kind of built-in floor beneath which nothing can be crushed further. Our own universe, under this picture, may have begun not from nothing, but from something collapsing before it. A big bounce would mean the Big Bang was less an absolute beginning and more a threshold, the far side of an earlier universe's final contraction. What we call the birth of everything might have been, instead, a rebound from a fall that started long before our clocks began. Roger Penrose, a mathematician and physicist, imagined something even stranger, an endless cycle of universes, each one giving way to the next. He called it conformal cyclic cosmology. In his vision, universes do not end so much as transform, their final stretched-out emptiness becoming indistinguishable, mathematically, from the dense hot beginning of another. The far future and the ancient past, in this model, resemble each other closely. The ending of one universe, in Penrose's vision, becomes the Big Bang of the next. As a universe expands and thins toward near-total emptiness, mass eventually stops mattering to its geometry, since nothing but light remains. That geometric sameness lets one eon's final moment be read, mathematically, as the very next eon's first instant, stitching endless universes together without any gap between them. Let your breath find its own unhurried rhythm now, without any need to guide it. Notice the exhale growing a little longer than the inhale, as though the body itself were choosing rest. Each breath out can carry a little more weight from your shoulders, your jaw, the small muscles around your eyes. There is no pace to keep. The breath already knows the way down into sleep. A boundary, according to certain models, separates black hole interiors from any universe born within them. That boundary would keep the two realms informationally apart, even as one gave rise to the other. The parent universe's inhabitants could never look inward and see what their black holes had produced. Whatever formed there would exist behind a threshold that light itself cannot cross outward. An event horizon marks the point of no return around a black hole, the boundary beyond which nothing, not even light, can escape outward. Cross it, and every direction that once led away now leads only further in. It is not a wall or a surface you could touch, simply a line drawn by gravity so strong that escape becomes, past that point, impossible under any known physics. An observer standing safely outside, in this scenario, could never witness a new universe taking shape within a black hole. Any light or signal from that inner birth would be trapped by the very horizon that made the birth possible. From our side, the black hole would simply look dark and still, hiding, perhaps, an entire unfolding cosmos we are permanently forbidden from seeing. Hawking radiation offers black holes a slow way to fade. Near the event horizon, pairs of particles briefly appear from quantum uncertainty, and sometimes one falls in while the other escapes outward. Over immense stretches of time, this steady loss of particles drains the black hole's mass. Given long enough, even the darkest giants could theoretically dwindle away to nothing. Stephen Hawking proposed this radiation in 1974, joining quantum mechanics to the physics of black holes for the first time. His calculations suggested black holes were not perfectly silent voids but faint, glowing objects radiating heat so weak it would be nearly impossible to detect. The insight reshaped how physicists thought about gravity, information, and the eventual fate of even the heaviest structures in the cosmos. For a black hole born from a collapsing star, evaporation would take longer than the universe has existed so far. Its radiation trickles out at a rate so faint that billions of years would barely register a change in mass. Long after stars stop forming and galaxies drift apart, these remnants would still linger, glowing so faintly they'd be indistinguishable from the surrounding dark. Placeholder: Mountain Party from 200 to Kreisau's. A newly formed universe would likely separate from ours almost the instant it appeared. Its own inflation would carry it outward at a pace that leaves ordinary space behind. Within a heartbeat of its creation, the new region could stretch beyond any possible reach. From our vantage, there would be no flash, no signal, nothing to mark its arrival. Because that separation happened so fast, causal contact with a new universe may be lost forever. No light, no particle, no trace of information could cross the widening gap. Physicists describe this as a horizon that forms almost the moment the birth occurs. Whatever happened there would remain unknowable, not through secrecy, but through the plain geometry of expanding space. James Hartle and Stephen Hawking once proposed that the universe may have no true beginning point at all. Their no-boundary proposal treats time, near the origin, as behaving something like another direction of space. In that picture, asking what came before the Big Bang resembles asking what lies north of the North Pole. There is no edge to find, only a smooth, rounded start. Let your body grow heavier now, resting deeper into whatever holds it. Feel your feet settle first, heavy against the sheets, unwilling to lift again tonight. That heaviness climbs slowly upward, through your legs, into your hips, spreading like warmth through your chest. Your shoulders sink next, then your arms, then your hands, until even your head feels cradled, full and still, wanting nothing but to stay exactly here. Certain theories suggest a universe could nucleate out of nothing, born from a quantum fluctuation. In this picture, existence itself flickers into being the way particles briefly appear from vacuum uncertainty. No cause pushes it forward, only the strange permissiveness of quantum rules. The mathematics allows it, though whether it happened this way remains an open question. Nothing, in this context, means something far stranger than an empty room. It is not vacant space, since space itself would not yet exist. There is no time to wait in, no place to appear from. Physicists mean the total absence of space, time, and the laws that usually govern them, a condition almost impossible to picture, yet mathematically describable. Quantum cosmology takes the strange rules of quantum mechanics and applies them to the universe as a whole. Instead of describing a single particle's behavior, it tries to describe every possible state the entire cosmos could occupy. This is an enormous leap from ordinary physics, treating existence itself as something with probabilities. The field remains young, its equations still being tested against deep uncertainty. The Wheeler-DeWitt equation attempts something almost impossible to imagine, a wave function for the universe itself. Rather than describing where a particle might be, it tries to describe every configuration the cosmos might take. Strangely, the equation contains no explicit time variable, which has puzzled physicists for decades. What time even means at this level remains unresolved. String theory proposes that reality has far more dimensions than the three of space and one of time we experience. Depending on the version, 10 or 11 dimensions may exist, most curled up too small to notice. In this framework, particles are not points but tiny vibrating strings, their vibrations giving rise to all known forces in matter. It remains an elegant, still unproven, attempt at unification. Within string theory, the number of possible vacuum states forms what physicists call a landscape, vast beyond ordinary comprehension. Estimates suggest the count could reach numbers called googles, far larger than the atoms in our observable universe. Each state could describe a universe with different particles, different forces, different constants entirely. It hints at a diversity of possible realities almost too vast to hold in the mind. Each vacuum state within that landscape could correspond to a distinct universe, governed by its own laws. In one, gravity might pull harder. In another, light itself might carry a different mass. Physicists picture these possibilities as valleys in a vast terrain of energy, each valley a separate reality with separate rules. Standing in ours, we see only one valley, though the terrain may stretch far beyond it. The string landscape lends mathematical weight to the old idea of a multiverse. If countless vacuum states truly exist, and each can nucleate its own bubble of space-time, then a vast collection of universes becomes a natural consequence rather than a wild guess. Theorists describe it less as one grand claim and more as an implication, quietly following from the mathematics itself. The scale involved stretches past ordinary imagination. Cosmologists exploring these ideas have proposed searching the cosmic microwave background for subtle, irregular patterns. If our universe once brushed against a neighboring bubble, the theory suggests, a faint imprint might remain, hidden in that ancient light. Detecting such a signature would require extraordinary precision. For now, it remains a careful, patient search through noise. Certain cold spots within the cosmic microwave background have been proposed as possible traces of ancient bubble collisions. These regions appear slightly cooler than their surroundings, and a few researchers wondered whether such coolness might mark where another universe once brushed against our own. The idea remains speculative, resting on subtle statistical hints rather than direct proof. It offers at most a whisper of possibility. Somewhere beyond the window, a low hum rises and fades, like a house settling into the night. Maybe it is wind moving through unseen branches, or a distant hum from some far-off road. It comes closer, then drifts away again, asking nothing of you. Let your shoulders sink a little further into the mattress. There is no need to trace where the sound came from, or where it goes. Only the drifting, and the dark, and the slow rhythm of your own breath beneath it. No confirmed evidence of bubble universe collisions has ever been found. The cold spots remain ambiguous, explainable by ordinary statistical fluctuation just as easily as by anything exotic. Careful surveys of the sky have found nothing that clearly demands a multiverse explanation. The question stays open, neither proven nor dismissed, resting quietly at the edge of what current instruments can measure. Gravitational waves may carry within them faint traces of the universe's earliest moments, back near the era of inflation. These ripples in space-time, if they exist at that scale, would have been stretched and dimmed across billions of years, yet something of their pattern might survive. Detecting them would offer a direct glimpse into physics from the universe's first fractions of a second. It would be, in a sense, listening to an echo far older than any light. In the year 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves directly for the first time. The signal came from two black holes, spiraling together and merging over 1 billion light-years away. It confirmed a prediction Einstein had made a full century earlier. The detection opened an entirely new way of listening to the cosmos, beyond light alone. Primordial gravitational waves, the kind thought to arise from inflation itself, have not yet been detected. Their signal would be far fainter than the ones LIGO has found, hidden within the subtle polarization of the cosmic microwave background. Instruments today are not yet sensitive enough to isolate them with certainty. Their absence in current data neither confirms nor denies the inflationary story, leaving that early chapter still unwritten. In 2014, the BICEP-2 experiment announced what seemed to be the first detection of primordial gravitational waves, a discovery that stirred excitement across cosmology. Further analysis, however, revealed the signal was better explained by ordinary cosmic dust within our own galaxy, scattering light in a similar pattern. The claim was quietly withdrawn. It remains a gentle reminder of how carefully such faint signals must be examined before they can be trusted. Plans exist for detectors placed far beyond Earth, drifting in space rather than resting on it. A mission called LISA, still in development, would use laser beams spanning millions of kilometers between orbiting spacecraft. Such distances allow it to sense gravitational waves at lower frequencies than ground-based instruments ever could. Massive, slow cosmic events, invisible to LIGO, might finally reveal themselves through this patient, distant listening. Rather than waiting for nature to reveal vacuum instability on its own, certain physicists have proposed forcing the question directly. High-energy particle collisions, they suggest, might briefly probe the shape of the vacuum itself under extreme conditions. The idea would be to test, in miniature and for an instant, whether empty space truly rests at its lowest possible energy. It remains a proposal on paper, not yet a method with clear experimental form. Despite decades of experiments and ever more powerful machines, no laboratory has ever produced even a fragment of new space-time. Every collision, every burst of energy released at facilities like the Large Hadron Collider has faded back into ordinary particles and heat. Nothing resembling a stable pocket of a different universe has appeared. The gap between theory and demonstration on this particular question remains entirely open. A handful of theorists have raised a more unsettling possibility, wondering whether pushing particle energies high enough could nudge the vacuum out of its current state. If our universe truly sits in a false vacuum, the worry goes, a sufficiently violent collision might tip it toward true vacuum somewhere nearby. The concern has never been dismissed casually, only examined with unusual care by those responsible for such experiments. Long before any collider existed, cosmic rays from deep space had already been striking Earth's atmosphere at tremendous energies. Physicists calculated the numbers carefully, comparing these natural impacts to anything humans could produce artificially. The collisions occurring overhead, far more energetic than laboratory experiments, have left no trace of triggered catastrophe across billions of years. Their calculations offered a kind of reassurance grounded in the sky's own quiet history. Let warmth begin low, somewhere near your feet, a mellow heaviness settling into the soles and spreading upward through the ankles. Let it climb through your calves, unhurried, pooling behind each knee like sunlight held in still water. Feel it rise into your hips, your lower back, loosening what the day left tight. Let the warmth continue upward, through your chest, your shoulders, down each arm to the fingertips, until every part of you rests in the same low glow, heavy, unbothered, held. Cosmic rays striking Earth's atmosphere have carried energies exceeding anything the Large Hadron Collider can produce, and they have done so for billions of years. Countless such collisions have occurred silently above every ocean, mountain, and city that has ever existed. None of them have unraveled the fabric of space-time or produced any detectable disturbance. The sky itself has been running this experiment far longer than any laboratory on the ground. This long, uneventful history of natural collisions has become one of the strongest arguments physicists offer for the safety of particle experiments. If energies far beyond human reach have struck Earth harmlessly across cosmic time, the reasoning goes, our modest colliders pose little additional risk. It is an argument built not on theory alone, but on the accumulated evidence of a sky that has never once betrayed catastrophe. Certain theoretical models place a strict condition on any imagined act of universe creation, one borrowed directly from ordinary physics. Whatever energy such an act required would still need to come from somewhere within the parent universe, obeying conservation of energy just as everything else does. A newborn universe could not simply appear from nothing without balancing books elsewhere. This constraint quietly grounds even the most speculative proposals in familiar physical law. In 1987, Alan Guth and Edward Farhi worked through the mathematics of creating a universe inside a laboratory with unusual rigor. Their calculations suggested that such an event, if it could ever occur, would not destroy the parent universe or explode outward. Instead, the newborn universe would inflate away almost instantly, severing itself from its creators. Their work remained theoretical, but it treated the question with the same seriousness given to any other physics problem. A physicist named Nobuyuki Sakai worked through models suggesting that universe creation might not need a singularity at all. In his calculations, space-time could curve and close upon itself smoothly without any point of infinite density. This would remove one of the most troubling requirements from earlier proposals. The mathematics remains speculative, but it offers a gentler doorway into existence than the sharp edge of a singularity. Certain models propose that electroweak vacuum bubbles could form, but only at energies no experiment could ever reach. The electroweak force, familiar from ordinary particle physics, carries within it a theoretical threshold for triggering such a bubble. That threshold sits so far above anything humanity has built that it functions more as a boundary of thought than a target for engineering. The idea survives as an equation, not as a plan. The energy scale required by grand unified theories dwarfs anything the Large Hadron Collider can produce by a factor of trillions. Where the collider reaches energies useful for studying familiar particles, unification physics operates near the edge of what mathematics alone can describe. Bridging that gap would require accelerators larger than solar systems, built with materials that do not yet exist. The distance between our machines and that scale is itself a kind of humility. Cosmologists have speculated that a civilization far older than ours might attempt to create a universe on purpose. Such a project would demand technology so advanced it barely resembles anything in current physics. It is less a prediction than a thought experiment, a way of asking how far intelligence might eventually reach. The speculation says as much about the limits of imagination as it does about the future. Such a civilization would need command over physics at the Planck scale, a realm far beyond anything humans can currently touch. At that scale, space and time themselves are thought to lose their ordinary meaning, becoming something closer to foam than fabric. No known technology approaches this level of control, not even in principle. The gap between our tools and that mastery is almost impossible to measure honestly. The physicist Freeman Dyson once turned his attention toward what intelligent life might accomplish across unimaginable stretches of time. He imagines civilizations reshaping stars, harvesting energy on cosmic scales, and outlasting the slow cooling of the universe itself. His speculations were playful but grounded in real physics, stretching imagination without abandoning rigor. They remind us that time itself may be the resource intelligence needs most. Somewhere above a still lake, mist rises without hurry, drifting upward until it disappears into the dark. It does not rush toward the sky, nor resist the air that carries it. It simply rises, thins, and is gone, leaving no trace of effort behind. Let your breath follow that same unhurried lift, rising and dissolving, again and again until sleep settles in like the last of the mist fading over still water. Certain models suggest that if a universe were ever created in a laboratory, its energy would not appear as an explosion at all. Instead, an outside observer might notice only a tiny, almost imperceptible increase in mass. The newborn universe would inflate away from its parent almost instantly, taking its vast expansion with it. What remains behind would look like nothing more than a whisper of extra weight on a scale. Even if such a signal could somehow be detected, no one knows how long it might take to reach us, if it ever could. The newborn universe would exist behind its own horizon, disconnected from ours in ways current physics struggles to describe. Some models suggest the wait could stretch toward infinity. Others leave the question entirely open. The silence that would follow such a creation might simply be permanent. Quantum gravity, the theory needed to fully describe how a universe might be born, has never been confirmed by experiment. Physicists have proposed several candidate frameworks, each mathematically elegant, none yet tested against observation. Without this missing piece, any account of universe creation remains an educated guess dressed in careful equations. The deepest question in cosmology still waits for evidence that has not yet arrived. Two frameworks describe the universe, and they still refuse to merge into one. General relativity explains gravity across galaxies and vast stretches of space. Quantum mechanics explains particles smaller than atoms with astonishing precision. Both have passed every experimental test given to them. Yet, where they should meet, at the birth of a universe or the heart of a black hole, their equations fall apart, leaving physics without a finished story. In laboratories far from any collider, researchers have turned to cold clouds of atoms to study the universe's earliest moments. These clouds, cooled to nearly absolute zero, are called Bose-Einstein condensates. Within them, particles lose their separate identities and begin behaving as a single quantum wave. Physicists have learned to shape these clouds into small stand-ins for early universe conditions, testing ideas that no telescope could ever confirm directly. Within these frozen atomic clouds, something remarkable can be coaxed into being. By adjusting magnetic fields, physicists can make the cloud expand in ways that mathematically resemble an expanding universe. Sound ripples within the condensate stretch and shift much like light does when space itself expands. It is not a universe being born, only its shadow, traced out in a puddle of matter colder than any place in the cosmos. From these same frozen clouds, another echo has emerged, one tied to black holes rather than expansion. Analog gravity experiments have produced sound waves that behave like light trapped near a black hole's edge. In certain setups, researchers have observed emissions resembling the faint radiation Stephen Hawking once predicted black holes should release. The resemblance is striking enough that physicists still study it for clues about a phenomenon never directly observed in nature. None of these experiments, however, create anything resembling real spacetime. What forms inside a condensate is a mathematical echo, not a fold in the actual fabric of the cosmos. The equations describing sound in a fluid happen to resemble the equations describing light near a horizon, and that resemblance is the whole of it. No new dimension opens. No universe stirs to life. Only numbers, borrowed briefly from one system to illuminate another. Away from any lab bench, a different kind of experiment takes place only on paper. Physicists sometimes imagine universes built to order, with constants tuned by hand rather than left to chance. What if gravity were slightly stronger, or the charge of an electron slightly different? These designer universes exist only in equations, yet they let theorists explore just how narrow the range of livable conditions might actually be. Each imagined adjustment leads back to the same quiet question: what allows anything at all to exist? Change gravity too much, and stars never form. Shift the strength of the nuclear force, and atoms fall apart before life ever begins. These thought experiments circle around what is known as the anthropic principle, the idea that the universe we observe must, at minimum, permit observers like us to be here to notice it. Let the muscles around your eyes forget what they were holding. There is no need to keep them steady any longer. Let the jaw loosen, the lips part just slightly, the whole face settling downward like sand, finding its own level. Behind your closed eyes, let the darkness widen, roomy and unlit, asking nothing of you. Your eyelids grow heavier with each breath, sinking a little further, until they simply stay. This same principle offers a quiet explanation for why the universe looks the way it does. We do not observe a universe hostile to stars or atoms or thought, because in such a universe, there would be no one present to observe anything. The reasoning is simple, almost circular, yet it carries real weight. Existence itself becomes a kind of filter, allowing only certain versions of reality to ever be witnessed. One number in particular refuses to explain itself. The strength of the force driving cosmic expansion, called the cosmological constant, sits at a value so small that no theory predicted it. Left to raw calculation, physics expects a number vastly, almost unimaginably larger. Instead, nature settled on something delicate enough to allow galaxies, stars, and slow evenings like this one to exist at all, with no accepted reason why. Physicists once tried to calculate the expected strength of this cosmic push using quantum field theory. The predicted number came out enormous, trillions upon larger than what telescopes actually measure. Nature's true value is almost impossibly small by comparison. No correction, no clever adjustment has closed that gap between prediction and observation. This gap between prediction and measurement has a name of its own. Cosmologists call it the cosmological constant problem, and it stands as one of the largest unresolved discrepancies in all of physics. It touches nearly every calculation about the universe's fate. Decades of work have narrowed many mysteries in cosmology, yet this particular puzzle has resisted every approach so far. To explain why this one number sits so precisely tuned, certain theorists turn toward the multiverse. If countless universes exist, each with a different cosmological constant, ours might simply be one of the rare ones where the value happens to allow galaxies and stars to form. No fine-tuner would be needed. Chance, spread across enough universes, could account for what looks like careful design. Not everyone finds comfort in that explanation. Critics point out that if other universes can never be observed or measured, the idea sits outside the usual boundaries of empirical science. A theory that cannot be tested, they argue, risks becoming untestable philosophy dressed in equations. The debate is not about the mathematics itself, but about what counts as a real scientific claim. Philosophers have joined this conversation directly, asking a deceptively simple question. Can a universe that leaves no trace, no signal, no possible observation still count as a genuine scientific hypothesis? Some argue that untestable ideas belong to metaphysics rather than physics. Others suggest that indirect reasoning still has value, even when direct proof stays forever out of reach. At the center of this discussion sits a standard proposed long ago by the philosopher Karl Popper. He suggested that a genuine scientific claim must be falsifiable, capable in principle of being proven wrong through observation. Multiverse theories, by their nature, often resist this kind of test. That single criterion has shaped much of the ongoing argument about where physics ends and speculation begins. Physicists on the other side of this debate offer a gentler defense. They note that inflation, a theory already supported by strong observational evidence, naturally predicts something like a multiverse as a consequence. If the foundation is testable, they argue, the conclusions built upon it deserve consideration too. Indirect evidence, in their view, still counts as evidence worth taking seriously. No resolution has arrived. Cosmologists continue to disagree about whether multiverse theories belong inside or outside the boundaries of testable science. The argument surfaces at conferences, in journals, in late-night conversations between colleagues who respect each other's work yet reach different conclusions. It remains open, unresolved, and strangely comfortable in its uncertainty, like a question the universe itself has not yet decided to answer. Notice your breath now, wherever it happens to be, not changing it, only following it, the way you might follow a slow tide moving in and out along a shoreline you cannot see. Each inhale arrives on its own, unbidden. Each exhale lasts a little longer than the one before, stretching outward, releasing something you were not even aware of holding. Let this rhythm carry you, breath after breath, further from thought and closer to rest. If humanity ever found a way to bring a new universe into being, the accomplishment would raise questions no equation could settle. Would the beings who might arise inside that new reality be owed anything from their makers? Would responsibility for their joys and sufferings fall to whoever triggered that first spark? Creating a universe, even in theory, carries a weight that reaches past physics and into the realm of conscience. Such questions echo an older debate in philosophy, one that predates any talk of baby universes. For decades, thinkers have asked whether our own reality might be constructed, rather than fundamental, layered inside something larger that observes us the way we might observe a bubble forming in a lab. The parallel is not exact, but the shape of the question rhymes across centuries, across disciplines, across quiet rooms where someone first wondered what lies beneath appearances. Nick Bostrom's simulation hypothesis, proposed in the early 2000s, raises a related question about realities nested one inside another. If advanced civilizations can build worlds indistinguishable from base reality, he argued, then simulated worlds might vastly outnumber original ones. The idea does not claim proof of anything. It only asks what follows logically if certain assumptions about technology and probability turn out to be true. A handful of theorists speculate that our own universe could itself be a created baby universe, budded off from some earlier larger cosmos. If eternal inflation or lab-based universe creation is possible in principle, nothing rules out that our beginning followed the same pattern elsewhere first. The thought is humbling rather than unsettling, placing our vast expanse of galaxies inside a lineage stretching backward beyond anything we can trace. This would mean our own Big Bang was an act of universe creation carried out by unknown agents, deliberate or accidental, somewhere beyond our reach. Perhaps a civilization triggered it, or perhaps it emerged from a natural process, no different from the ones cosmologists already study close to home. Neither possibility can currently be tested. Both remain thoughts held loosely, offered without certainty, resting at the edge of what physics can presently say. No observational method today can distinguish a universe that was created from one that arose entirely on its own. The light reaching our telescopes carries no signature marking its origin as deliberate or spontaneous. Whatever mechanism gave rise to the Big Bang, it left behind a glow that looks the same either way. The instruments cannot yet ask the question, let alone answer it. All the evidence gathered so far remains consistent with a single natural origin for our universe, one requiring no outside creator or hidden architect. The cosmic microwave background, the abundance of light elements, the patterns of expansion, all fit comfortably within known physics. Nothing observed demands an external cause. The simplest account still holds, even as theorists continue to wonder what else might be possible beyond it. Future telescopes, among them the aptly named Extremely Large Telescope, now under construction in the mountains of Chile, may refine our measurements of the universe's basic parameters. Sharper images of distant galaxies could tighten estimates of expansion and composition. Each incremental gain in precision narrows the space where old questions can hide. The instruments grow larger, the mirrors grow wider, and the sky grows very slightly more legible with each passing decade. Improved measurements of the cosmic microwave background's polarization could, within decades, better test the predictions of inflation itself. Faint twisting patterns in that ancient light, called B-modes, might one day reveal traces of gravitational waves from the universe's earliest moments. No detection has yet succeeded, but each new instrument reaches further into that fainter signal, patient in a way that mirrors the patience the universe itself has always kept. Whether humanity could ever witness the birth of a new universe remains one of cosmology's deepest open questions, unanswered and perhaps unanswerable within a single lifetime. And so we return gently to where we began. Beneath every equation and every telescope lies the same old wonder that first lifted human eyes toward the night sky. That wonder is enough. Let it settle now, like starlight on still water, asking nothing more of you than rest. Good night.